Hello, this is going to be the first lecture on analytical chemistry covering the analytical process, including some of the key tasks that analytical chemists produce and provide every day. So what does the analytical process actually involve? So it's kind of looking at the analytical chemist's job, what tasks do they do, what kind of outcomes do they achieve, and how they can help in both a chemical lab and a business setting. And then we'll be looking at the general steps involved in a chemical analysis, which typically falls under the job description of an analytical chemist. So what is an analytical chemist's job? So typically they provide two types of analysis. One is quantitative analysis. So this is looking at how much of a chemical substance is present. And the other is qualitative analysis, i.e. what chemical substances are present. So one looks at the amount and the other one looks at what is present. So the chemical measurement is only part of the analytical chemistry process that starts by asking a meaningful question, collecting a relevant sample, creating a measurable sample from this, making the measurement, interpreting the results, and creating a meaningful report. And so all of these steps combined together are effectively what we call the analytical process or the analytical chemistry process. So in a typical analytical chemistry process, we start by asking the question. So this is, what do we want to know when we finish this process? Oftentimes, this is sort of to look at the caffeine in coffee bean, or the amount of caffeine in chocolate, or the amount of mercury in a fish sample for export, things like that, to ensure that products that reach the consumer or products which are used in a chemical lab are indeed up to the quality and purity that we expect. Then as the second part, we have to select appropriate analytical methods. So usually these are based on what might be best for the analyte in question, i.e. that which we want to find out and measure. But sometimes they are dictated by what we have available in our lab or what we have available in our business or via outsourcing to other analytical chemistry labs. Then we look at sampling. So this is particularly important in cases where we have heterogeneous samples. In the case of homogeneous samples, it's also important to have a good rationale for our sampling, but typically it's easier for homogeneous samples. And generally that's what we'll be discussing as we go through this lecture. Then we'll be looking at sample preparation. So how do we go from the sample that we take from our substrate in question, and how do we go from that to creating something which can actually be measured? Typically, this involves dissolution of the sample in some sort of a solvent, as it's often easier to process liquid samples compared to solid or gaseous samples. Then we look at analysis. So this is the process of actually measuring the sample, whether that be quantitatively or qualitatively. Then after we have obtained our analysis and we've ensured that it is robust and that it is reliable, then we move on to reporting and interpretation of our results. So this involves writing a report, which will be read by others, but also providing a unique insight that comes from the knowledge of the analytical chemist, and trying to make that as approachable and as universal as possible. And then after that, conclusions can be reached. And so this is often out of the hands of the analytical chemist, although the recommendations of the analytical chemist are used in reaching those conclusions. This could be in saying that, for example, the fish sample is suitable for export because the mercury levels are low. Or it could be saying that we have too much caffeine in our coffee beans. We need to put a warning here to ensure that people don't overindulge in caffeine, things like that. So the first part, asking the correct question. So this is really just, what do we actually want to know whenever we're measuring our, for example, chocolate sample, as we will discuss here. We're interested in the caffeine content. So that's our question. We want to know how much caffeine is in a particular chocolate bar. We could also be asking how much fat or how many fat solids there are, what's the concentration there, or asking how much sugar there is, things like that. It just depends on the question we want to answer, because that will dictate which methods we will use and how we will prepare our sample, and also what conclusions and recommendations we make at the end. So we select analytical procedures. As I've said, the first step is to generally search the literature for analytical methods. This is a good time to use things like keywords. In the case of our caffeine and chocolate bar experiment or analysis, we could use the words caffeine and chocolate bar. We could even use potentially the words analytical procedures or things like that. And typically we'd look up and find or try to find a suitable standard procedure for this, so that at least we know that there is some previous history which indicates that this process that we're about to undergo will work. So we need to also ensure that the method chosen is suitable for our equipment. So for example, it's no good selecting a HPLC based method if we don't actually have such equipment in our lab or available to us. These are some of the things that we have to consider. So we have to choose an appropriate method. Oftentimes it's not possible to choose an HPLC method because of expense or unavailability of a suitable column, things like that. Maybe we don't have enough capital expenditure in our business to be able to buy one or even to outsource it to another analytical lab. If there are no suitable methods, it may be necessary to devise one based on similar methods. Perhaps someone else has determined the caffeine content in a different solid, maybe like cacao or cocoa, something like that. Then we move on to sampling. So sampling is the process by taking something from our raw material, our sample to be analyzed, and getting something that can actually be measured. So sampling is the selection of a representative material to analyze. And it's important that this is in fact representative, that it does in fact represent the overall total of the material, that if we take a little bit of it, it still acts and behaves in the same way as the bulk. Proper sample selection ensures meaningful results, because if we don't choose our samples correctly, we'll effectively get meaningless results at the end. And so it means that our whole process that we've gone through will have been pointless, will have wasted time and resources. To properly understand caffeine levels in chocolate, for example, and to make broad sweeping statements about caffeine in chocolate, we would need to analyze many different types of chocolate, for example, dark chocolates, milk chocolates, white chocolates, and so on. Maybe from different manufacturing processes and things like that. And by comparing those results, we would then be able to make broad statements about caffeine levels in chocolate, and those could be potentially used by legislators to drive recommendations and regulations on food safety. In a pure chocolate bar, it's typically homogeneous. So this is one that's just made of chocolate. Typically through the process of making chocolate, you melt the chocolate first at a set temperature, and then you pour it into a mold, and then you cool it, which will give you the chocolate bar. So in those pure chocolate bars, they're reasonably homogeneous, so the composition is similar throughout. So we don't need to be particularly careful about our sampling in this instance. No matter what part of the chocolate we'll take, we can be pretty sure that it'll be representative of the whole system, but we should still make sure that we adhere to proper, robust sampling methods. So chocolate with nuts is a heterogeneous material because of the nuts that are present in there. They aren't mixed perfectly through the chocolate. And so that results in this heterogeneous material where one part is pure chocolate, one part is pure nut, but overall it makes a chocolate bar with nuts. And so their composition is going to be variable throughout. So here are two different types of heterogeneous material. One on the left is a random heterogeneous material here, where we have this outer square is sort of like our area of our sample, which is randomly heterogeneous. What we can do here is we can divide the sample up into a certain number of squares, and then using a random number generator and assigning numbers to each square, we're able to randomly pick some numbers, or randomly pick some squares, and we take our samples from those squares. And that should be, if we take enough squares from a random enough array of positions, we will get a representative sample. In the case of a segregated heterogeneous material, so this one is divided into 4 areas, A, B, C, and D. They have different compositions. A is about 3%, B 5%, C 10%, and D 82%, it would mean that we would have to take 82% of our squares from the region of D, 10% from the region of C, 5% from the region of B, and 3% from the region of A. So if we had 100 sampling squares, 3 of them would be in the A region, 5 of them in the B, 10 of them in the C, and 82 in the D. And this would help us to ensure that our sample is going to be representative of the entire raw material, the bulk sample. So in the typical analytical chemistry process, we go through sample preparation. So sample preparation makes the representative sample measurable. So this usually involves dissolving it in some sort of a solvent, as I've said. In the case of our chocolate bar, it's not going to go through a liquid chromatography machine very easily as a solid. And so what we can do is we can dissolve some of it into a solvent, and we can pass that through our column. So low analyte concentration can be overcome by concentrating the sample. So for example, if our detector is unable to, if we know that we have an analyte in our sample, but our detector cannot detect that, our machine is not capable of getting it, we can overcome this by concentrating the sample. And so as long as we know what we're doing and the procedures that we're undertaking, that can be an okay change to make. It may be necessary to remove or mask species that interfere with the chemical analysis. So in the question that we asked at the start, what we were interested in was the caffeine in chocolate. Now, unfortunately, chocolate also contains fat molecules, and those typically interfere with the caffeine in such a way as to bias the results or change the results that we'll get at the end. And so it becomes necessary to remove that fat from our sample. Now, this won't change the amount of caffeine we get out at the end, but it will mean that the caffeine that we measure will in fact be reliable. And so for the chocolate bar, the sample preparation consists of, as I said, removing the fat because it interferes, and dissolving the desired analytes because a liquid sample is typically a lot easier to measure than a solid sample. So the first step in the general method that was first developed for caffeine analysis of chocolate is to grind up the chocolate bar into fairly uniform pieces, at least very small pieces. Now, the problem with chocolate is that at room temperature, under the stress of the pestle on the mortar, it would kind of become a paste. It would kind of melt a little bit. It wouldn't really form the little particles that we need. And so to overcome that, one of the ways that the first people to do this, what they suggested was that instead of just grinding it up at room temperature, what you do is you first freeze the chocolate bar to make it more brittle, and then you would also freeze the mortar and pestle. And then once they've reached a cool enough temperature, you would take it out, you would break it up into little pieces. And then if it starts to become paste-like, you put it back in the freezer and repeat that process until you've reached a point where you feel that for the most part, the particles of the chocolate are reasonably small. And of course, the reason that that's done is to ensure that the particles are quite small and that they can be easily reached by the solvent, so that any caffeine which is in the chocolate can be dissolved out of the chocolate into the solvent, or extracted out of the chocolate into the solvent. So if, for example, here, what we've done is we've gotten a centrifuge tube, we filled it with our chocolate, which has been ground up into tiny particles, and we've added some solvent here. And our first step is, as we mentioned earlier, is to prepare the sample, but we need to remove the interfering particles first, the interfering molecules, which are the fat molecules. So we have our finely ground chocolate, which we've spent considerable amount of time grinding. And then the solvent here is going to be petroleum ether, or really any solvent which will dissolve the fat whilst also leaving behind the caffeine. So we shake this well to create a solid suspension in liquid. So initially we'll have a colorless PET ether layer and the chocolate in the bottom. We'll shake this up and we'll get like a suspension of the solid chocolate particles in the liquid, and it'll be kind of like a cloudy brown color, a bit cloudy like milk, but cloudy brown instead of white. Then we centrifuge this. This will separate the solid particles from the liquid particles, and it will separate into two phases. So we'll have a solid residue here, and we'll have a supernatant, which is this liquid above the solid phase, which will have the dissolved fat. So the fat will have been extracted from the chocolate into the solvent. Then we centrifuge that to separate the two layers. Then this layer contains the fat. And what we can do is we can just decant that off so that what we're left with is this defatted chocolate residue. So we've gotten rid of the interfering species. Now we can move on to try and obtain our caffeine from the chocolate, because ultimately whilst this is defatted, so it doesn't have the interfering molecule, it's still not in an appropriate state to measure analytically. So transferring from this centrifuge tube, what we do is we transfer this chocolate with water into an Erlenmeyer flask, and we kind of boil the water inside this flask. We try to swirl it and mix it so that the particles are suspended in the water. And what this will do is it will help to extract the caffeine into the water. So the defatted chocolate is suspended in water, as we've said here. We kind of boil it. We mix it up for a while until we believe that everything has been properly extracted. Then we transfer that to another centrifuge tube. Then we centrifuge it, and that will separate the two layers from the chocolate slurry and the solvent. So this supernatant then contains the analyte, which in the case of our chocolate example is going to be the caffeine. And it also includes little tiny particles of chocolate. So some of the very, very small ones that we have created through this process. Maybe we don't really want them to be there, but they're there nonetheless, and they won't really settle. At least it'll take a very, very long time for them to settle. And we don't really often have enough time for that to happen. Even with centrifuging, some small particles still remain suspended in the liquid because they're lighter than what gravity can affect. So the next step then is to remove these tiny particles through a physical process called filtration. So we filter that. So what we do is we transfer this supernatant liquid to a syringe, and then on that syringe, we will affix a tiny micropore filter, which will twist onto the syringe and will secure quite tightly. Then we pass through the supernatant liquid, and it will leave behind the tiny particles, which will get stuck in the filter. And then the liquid that comes through will be free of those tiny particles and will be in a state which can be measured analytically. So here we have at the bottom the filter solution prepared for the chromatograph, and we have here the filter. So it's this little brown or gray thing there. So that's a micropore filter, which is very, very useful for these sorts of processes. So we've gone through our sample preparation there pretty easily, but that was the old traditional method, which was devised before a more modern sample preparation technique called the solid phase extraction. And this is something which simplifies our sample preparation. It utilizes a disposable cartridge, which can separate the solids from the analyte from the interfering components, and it can be utilized in many different ways. So this SPE, this solid phase extraction, separates some major interfering components from the desired analytes. It's not a perfect situation, it's not a perfect system, but it is a lot faster, it's a lot easier to do. So an SPE cartridge is a short disposable column containing a chromatography solid phase. And so for the chocolate sample, SPE separates caffeine and theobromine from sugars and fats in the chocolate. So using this SPE process, what we first do is we condition the column using a polar solvent such as methanol, the CH3OH, and water. This will the conditioning of the column will be done first with this to sort of like flush out the solid phase of the chromatography cartridge. Then the water will be added to wet the system with a polar solvent. Then we add our crude sample, and we have that will form a layer on top. And because of the nature of this chromatography medium, we will see that some of the particles in the crude sample will adhere more strongly to it. So they'll interact more strongly. Some of them will form stronger bonds to the material, and so they will get stuck in the column for longer. Then once we have all three into our chromatography medium, what we can do is we can add a solvent. So in this case, we'll add a solvent for the sugars, which will elute the weakly bound solutes. So that the fat will get stuck, which is the square. We'll leave behind the caffeine first, and then we will add a solvent which will elute the weakly bound solutes, which is in this case the sugar. So all the sugar gets flushed out, leaving behind the fat and the caffeine, and also the theobromine, because it's typically quite hard to separate. But as we'll see later, it's not a huge problem. Then what we can look at is a solvent which will extract the caffeine from the chromatography medium. And then this will give us a solvent which contains our caffeine, which is what we're interested in, what we're trying to measure, leaving behind the fat in the cartridge. And then since the cartridge is disposable, we can just dispose of the cartridge. So that's the general SPE method. So you can see it involves a lot fewer steps, although these cartridges can be difficult to source and can be quite expensive. But they are a much easier way to do this. So the typical analytical chemistry process. So analysis is step 5. So this is where okay. So we've asked our question, we've gotten our sample, we've prepared our sample. Now we need to actually use the method that we decided on back in step 2. And so this is our analysis procedure. So we will inject the solution into a chromatography column, which separates the analytes and measures the quantity of each. And so that will give us our concentration. The concentration of the analyte is measured in several identical aliquots. So we need to take a few measurements in order to make sure that we account for any variance. So repeat the measurements using different aliquots several times to assess uncertainty or variance in the samples, because we could have randomly either a bad measurement or a bad sample. And so if we only do one, we could end up with biased results, which are not actually representative of the system. And so typically we do at least 3, preferably at least 5 measurements with 5 different samples and aliquots. So the uncertainty of a measurement is as important as the measurement itself because it indicates the measurement reliability. Use of different analytical methods can identify any bias. So here we have a typical setup for a sort of a column chromatography system. So we have here a packed column, which the different components in the analyte sample or analyte solution will interact differently. And so they will pass through this column, which is quite long, maybe several inside of an HPLC, maybe several meters long. It's all coiled up. So we'll inject this solution. The different analytes will move through it at different rates. And so that separation in time and space will mean that they will exit the column at different times. And so hopefully they will be what's called separated. And so that whenever we detect them using our UV lamp at a particular wavelength, what we detect will only be the analyte that we're interested in. And so that will enable us to actually measure the concentration which is present. So we inject the analyte solution, it passes through the column, gets separated in time, and then passes out as solvent out at the end, which is typically just, since we're working with very small quantities here, it's typically just disposed of. So inside this column, we have what is called modified silica. So it's a silica bead, which is has hydrocarbons appended to it. And so that will cause polar and non-polar molecules to pass through the column differently. So here we have our column, which has had the analyte solution injected into it. And so we have this blue and this red line, which will represent our 2 different analyte species, the caffeine and the theobromine in the case of our chocolate sample. So initially they are injected together, but over time and due to their differing interactions with the modified silica, what we will see is that there will be a separation in time of the 2 samples. So as we continue to pass the two different analytes through the column, they will separate. So initially they're together, and so they would overlap with each other, and it would be quite difficult to determine which signal is coming from which. But because of the separation in time, you can see that the red line and the blue line are quite separated towards the end. We will be able to measure them independently of each other. And so that means that we can be fairly certain that what we detect using our UV lamp and UV detector is going to be each one of the two analytes. So we'll have a peak for theobromine and a peak for caffeine. So here we can see our two different peaks for our two different analytes. So we have an analyte here, which is coming out first, which is our theobromine. It's labeled peak A or theobromine. And then we have here our caffeine, which is this star. So this comes out after some 2 or 3 minutes after the theobromine. And so this good separation here in this idealized chromatogram means that we will see that the two analytes have different detector responses. And so that means it's kind of hard to say which one is in higher concentration, because the detector response for each one can be different. Like it could be that the detector is more responsive or measures a higher intensity for theobromine versus caffeine for a similar concentration. And so for that reason, we need to create what is known as a calibration chart. And this calibration chart will help us to rationalize the peak areas or peak heights to their relevant concentrations by utilizing a system whereby we measure solutions of known concentration of both theobromine and caffeine, or whatever our particular analytes may be. So in this case, we look at analysis calibration curves. And so going back to what I mentioned a moment ago, I said detector response usually varies with analyte type. And so that means that for two analytes of the same concentration, one can have a higher response in the UV detector. And this is really just a function of the measurement types and the way that they work. But we can overcome this problem relatively easily using calibration curves. So detector response must be measured at different analyte concentrations to ensure reliability. And this will also help us to formulate a correct concentration for our unknown sample, which is in this case our chocolate bar. And so detector response as a function of analyte concentration is called a calibration curve. So we will plot on our y-axis detector response, and we will plot on the x-axis the concentration of the analyte. And so that will give us an idea of if we have a certain height of peak in our chromatogram, we can relate that to a specific concentration. So standard solutions of known concentrations of pure analyte are injected into the column and measured. So we'll make up a solution of our caffeine with different concentrations, maybe 1 ppm, 2 ppm, and so on, and then measure the height as it passes through our apparatus on our instruments. So the relationship should always be linear, enabling determination of unknown concentrations. And we will find out in later lectures what happens if the calibration curve is not in fact linear. So here is an example of calibration charts. So we can have here one for the caffeine and one for the theobromine. And we can see that the detector response at the same concentration is going to be greater for the theobromine. And so that helps us to know that even though the peak height in our idealized chromatogram earlier was much higher for theobromine, maybe the concentrations of theobromine and caffeine were quite similar. So if we have some unknown, for example, in the case of theobromine here, we have a peak height of 11, we can find out what the concentration might be. So if the peak height is 11 centimeters, we find out that the concentration is around about 5.5 ppm of theobromine. You can do the same thing for caffeine. Say we have a peak height of around about 3 centimeters, we would find that we have a concentration of around about 7.5 ppm of caffeine in that particular sample. So after we have obtained the results for all of our different replications and our different samples, what we can do is we can formulate a report and interpret the results to give a recommendation to other people so that they can be informed of what exactly is going on in the bulk sample. So reports should always be concise, clearly written, and easily understood, because remember, not everyone who reads your report is going to be totally familiar with everything you did. Even people within your same lab or in same business might not know exactly what you did because they were not the ones to do it. And so whenever they read it, they should know exactly what you did, how you did it, and how you reach the conclusions that you did, so that they themselves don't have to do the measurement, or they themselves don't have to study in detail this analytical chemistry process. But it's important that everyone in the hierarchy, everyone involved with the report should be aware of what happens in a typical analytical chemistry process. So we should also note in the report the limitations of the analysis. The report should be audience appropriate as well. So that means that we shouldn't use too much technical jargon whenever we're discussing this report or writing a report for people involved with marketing, for example, or management or exports. They should be given the information that relates to the variables which are going to be important to them. So for example, they want to know if the caffeine is within the allowed range for caffeine in chocolate bars. If it's the case of mercury in tuna, they want to know, is it below what is the maximum allowed concentration for export, or is it going to have to be utilized in some other way for some other means? Those are things that should always be considered when the report is being written. Is it going to be audience appropriate? And then the last one is sometimes the analytical chemist is sometimes involved with this last one, which is drawing conclusions, but not always. Typically, this is utilized by someone making use of the analytical chemist report. So it can be after the drafting of the report, the results are often used by others. So it could be utilized by marketing executives. It could be utilized by people involved with import export. It could be utilized by people managing the raw material supplies for a factory. Could even be used by lawmakers and regulators to come up with new regulations on, for example, food safety or chemical purities and things like that. So a well-written, clear report is going to be less likely to be misused or misinterpreted. And so that's the last thing that we want. We want always to have a report which can be accepted and is not going to cause a dip in consumer confidence, or it's not going to maybe create unintended consequences. So going back to our caffeine problem that we talked about initially, we can see here that caffeine can really vary and is present in quite a few different types of food and drink. So typically, whenever we think of caffeine and beverages, it's always coffee that we think of, but coffee is not always the only drink that we might drink which has caffeine. So coffee here, espresso, has about 40 milligrams per serving, but the serving size is quite small. So it's really quite concentrated in caffeine. Drip coffee is has a high number of caffeine, or high concentration of caffeine, but serving size is quite large. Black tea, green tea, they also have reasonably significant amounts of caffeine, about a quarter of what would be present in the similar amount of coffee. Which is not insignificant. Cocoa has about 2 milligrams per serving. Milk chocolate, dark chocolate, which is high in cacao, has actually a considerable amount of caffeine. Actually, the amount of caffeine in dark chocolate can exceed that in coffee. So you can see that here the serving size is about a third larger than the coffee espresso, but in fact the caffeine amount here is more than a third higher. But analytical chemistry is something which can give us values for all of these. So in summary then, so we look at analytical measurements as being only a part of the process. We also have asking of the question, we have report writing, we have analysis, we have sample preparation. It's really a much longer process than maybe is often realized. So we need to formulate the appropriate question first. Samples must be properly handled in order to obtain meaningful results. So that means if we don't sample properly, we won't have a representative sample, and that means that our results are effectively meaningless, and the whole process is tainted by this, and so it's just meaningless results. So we end up just having to throw everything in the trash can and move on to the next measurement and measurement process. So the reporting of results needs to be accurate and unbiased to avoid misuse, because the last thing we want is a dip in consumer confidence in the product that we're involved with, or we don't want regulators to misuse our reports and regulate something which is doesn't need to be regulated, or for them to believe that something that does need to be regulated is safe. So these are all things that need to be considered. And so this brings us to the end of this part. So thank you for listening. I hope you enjoy the next part.